This video discusses fluid power systems. So we're going to look at fluid power system models, characteristics of fluid flow, principles of fluid power, components, and also some hybrid systems. There are three primary power sources, as we've discussed before, that we can use for robotics. We use them to move the robotic arm, we use them to actuate production tooling, and to power the robot's controller. Now, those three types of power sources are hydraulics, pneumatics, and of course electric. We've already discussed the electric. Alright, so for hydraulics we have Pascal's law. Pascal's law is the principle behind fluid systems, and it basically states that pressure applied to a confined fluid passes undiminished throughout the fluid, so that we have the same pressure anywhere within the fluid. Given that, we can determine the force. So if we look at the force, force is the is measured in the SI units, which is basically the world units of System International is what SI stands for, and the force is given as Newton. In US, we commonly use the old British imperial form of pound to measure force. Okay. And so when we start talking about pressure, pressure is force divided by an area. So we can either measure force in something like pounds per inch squared, or PSI, pounds per square inch, or in the SI units, the units of force or units of pressure are measured in Pascal. And so Pascal is the Newton divided by the meter squared. Now 1 PSI, 1 pound per square inch, is about 7,000 pascals. So commonly when we talk about force, we're actually talking about thousands of pascals, so they use kPa, kilopascal, to measure that. Alright, so the main purpose of the power source, as we've discussed before, is to use an actuator to make something work. So an actuator is a device that converts energy into motion. It can be linear motion or rotational motion. So here's a picture of a hydraulic actuator, sometimes or typically referred to as a cylinder or hydraulic cylinder. And the idea here with this is that we put pressure in. So we put pressure in here, or put oil, would put high pressure fluid in here, and it pushes the actuator down and pulls it into the cylinder. Or we can push hydraulic fluid down on this lower side down here, and that will then push the fluid, will then push the hydraulic cylinder out and make it extend. So typically on our robot axes we use electric servo motors that we discussed before, unless the robot is really large trying to move very, very heavy loads. So if we have to move very, very heavy loads, that's where hydraulics comes into play. For production tooling, we typically use pneumatics. Pneumatics is very common to activate grippers and other types of devices, but we can also use electric grippers, or welding, or those sorts of things would be activated a lot of times through electric. Alright, so just to kind of give you an example of the type of power that we can use, here's what a robotic arm, this is over in the Netherlands. It was built in 2000, so it's about 20 years old now. But this is a bridge across the river. As you can see, a boat going underneath there. And of course, to lift such a large structure, they make use of the hydraulic power. Alright, so let's look at force and pressure and area. So remember that pressure is defined as the force divided by the area, or we can state it the other way and say that the force is the pressure times the area. Okay, and so force, again, it has units of pounds. Area is inches squared, and so the pressure then would be pounds per inch per square inch, psi, or pounds divided by inches squared. Okay, or we can do the SI units and do pascals and newtons and meters. All right, but so how does this work? Well, if you look here, if we have a closed-in area, remember Pascal law talked about a closed-in area. So if we have this closed-in area here, and on the left side I have 1 square inch, so the area of this, I have 1 pound pushing down on 1 square inch. And but using Pascal's law, that 1 pound per square inch is everywhere throughout this entire cylinder, or this entire system here. And so on this side I have 25 square inches. Alright, so I have the exact same the 1 pound is basically activating it here, but the 1 pound is pushing down on 1 square inch. And so over here I have 25 square inches, which means that the force being pushed up then is 25 pounds. And so this is how we can lift very, very heavy loads, by using effectively this amplification method. By increasing the area, we can apply a small force over here to a small square inch area, and then have a much larger area here, and therefore increase our force. So this is of course the way even like a hydraulic jack you might use to lift your car works. Okay, some drawbacks of hydraulic systems. Okay, hydraulic systems are very complex. They require a oil supply reservoir, so you got to have a large reservoir to supply the oil when you need it, and when you're and to put it back as you're returning the system. You got to have a pump to generate that pressure. Somehow you got to generate that pressure, so that's what the pump does. Then you're going to have piping to pipe the oil to where it is that you need it for your activation. You're going to have control valves to control it, and then of course your actuators, which are actually doing the motion. Okay, so issues with this then: it's a high maintenance system. It requires constant repairs and cleaning. The oil can leak, and when it does, it obviously causes like a slippery floor, but it can also cause a fire, so it can be very, very dangerous. Alright, so here's just a typical layout of a system here. On the left we have our pump. So over here we have an electric motor driving a pump to generate the pressure. So we have the oil coming from a tank. Underneath of the pump is our tank, and so we're pumping this out. And so here we have our high pressure supply, coming over, and then we run this through a valve, and through the valve we're then running it through an actuator. This is a linear actuator to get linear motion by you pushing the cylinder in and out, as I discussed before. And then over here we have a second valve that we can use to control a rotary actuator. So you can have hydraulic actuators that actually give you a rotational motion as well. So the control valve here, there's a couple of videos that I have here. There's a couple of links in these slides. You want to follow these and watch these videos because they do a really excellent job of animating the way that the control valves work. So check out those videos and follow those. Those are very nice. Okay. So, but here I'll just try to walk you through it. This is a simple control valve. It is a two-way, or it's a two-way valve, meaning that it's basically got two ports. Sometimes they call it a two-port. You have what they usually call port A, and if you have multiple ports, A, B, C, so you have port A, and then you have your pressure port here. And so the way this valve works, right now the default position has that this area of the valve at port A is blocking any flow of the hydraulic fluid. So right here we're pressure is trying to come in port A, but it's being blocked. And so when you push in the valve, so if you push in the valve, red valve handle over here a little bit, you push that in, then that's going to allow fluid to flow up through here. Actually, excuse me, the pressure is flowing through the pressure port. So this is the pressure coming in through the pressure port, and then it's going to flow out through port A if we push the valve. So with the valve not unpressed, with nobody pressing the handle, the spring is keeping this pushed over, and so there's no flow in through port A into the system. But when we press the red handle and we press this in, that allows the pressured fluid to flow through the valve and out port A. And so this is a schematic. Down here at the bottom is a schematic, so showing you the spring. So this is the spring over here, and then of course this is the manual activated handle. And what it's showing you here is that the fluid is being blocked. So here with these are blocked, so there's no flow. And then when you press it, when it's pressed, and so it's in this position here, then you're going to have flow through the valve. And again, there's a link there that you can watch. Alright, so this is a slightly more complicated system with a three-way valve, but two position. So we still have two positions on this, but we have three ways that fluid can flow. So here we of course have our pump generating high pressure coming into the pressure port. Okay, so the fluid is always coming into the P, or the pressure port. Now with the spring pushing this valve up, okay, then there would be no pressure in the pressure port here, and so it's being blocked. So the pressure port is being blocked, and then gravity would be pulling down the cylinder and allowing the fluid to flow back through port A, and then through the exhaust. The E stands for exhaust, so through the exhaust and back into the tank. Okay. So basically gravity is what is going to pull this cylinder back. right? But in the drawing shown here, somebody is already pushing down on the handle, so it's in the second position, which allows pressure to flow through the valve, through port A, into the cylinder, and push out the cylinder and make the cylinder go up. Okay, so again, once pressure is relieved, gravity pulls the cylinder back down, pushing the fluid backwards in the opposite direction, as I've got shown here, through the exhaust and through the tank. So this slide is basically just trying to walk you through what I showed you. The only difference here is that we have an electronic solenoid now down here, so that when you engage the solenoid, that's what makes the valve open or shut. So it's using an electronic solenoid to push the valve into the second position. Alright, so if we're reading a schematic, this slide's here to help you understand the how to read a schematic. So this is a 5-port valve. We have an A port and a B port, and then we have our exhaust A, we have our pressure port, of course, and exhaust B. So and when you look on the left side, instead of having a knob to be pressed, we actually have the electronic solenoid. So this here is what the electronic solenoid looks like in the schematic form here. So here's our solenoid. So when the solenoid is energized, this is pushed over to the right. So pressure coming from the middle goes out port A into an actuator, and there's nothing going through the exhaust A, but pressure is coming into B and then going into exhaust B. And then when the solenoid is released, electricity is removed from the solenoid, the spring pushes it back into the position shown here, so that the pressure that was up in A is now allowed to come back through exhaust A, and pressure from the pump is fed over to port B and pushing, basically going to activate an actuator in the opposite direction. Alright, so the T symbol here shows that the port is blocked or closed, not allowing fluid to flow through that port. And of course the arrows are indicating the direction of flow when it is allowed to move. Alright, so our key parts of the hydraulic system. Okay, we have our directional control valve, which we were just discussing. We have our supply pressure, P. We have the T for tank, and E for exhaust. Exhaust means that you're releasing that back into a tank. And then A and B are the working ports that are going to be connected to the actuator device. Alright, so this is a 3-directional control valve here. The way this one works, you see the moving cylinder actually has 2 kind of blocks to block the fluid there. So we have the tank or exhaust. So sometimes you see E, sometimes you see T for exhaust. Exhaust is going back to the tank. You have your A port, your B port, and then your pressure. So pressure is coming in here. So pressure is going to come in here. Now when this solenoid is not activated, then there's actually 2 solenoids on this, one on the left and one on the right. So when it's not activated, it's in the middle and the pressure is blocked and there's no flow. When you activate the solenoid on the left, this moves over to the left. which allows pressure to come over here and then flow through port B. Okay, so when that happens, then pressure coming out of A can then return to the tank. If we activate B, then it's just the opposite. B gets the pressure, or excuse me, A gets the pressure and B releases back into the tank. So I got another graph showing you that here, and I think this is showing you the middle position. This is showing you it's energized, which is allowing pressure to go to port B. Okay, so it's allowing, here the pressure is going through port B. Right here, pressure is coming up through the pressure port and then back down through B, and then any pressure in A is being released back to the tank. And then if we energize it over here on the other side, it's allowing the pressure go into A, and then B releases the pressure back into the tank. Alright, so there's just a close-up of the schematic drawing of this valve. Okay, so each box is referred to as a position, and each open spot that we are going to connect either the A and the B to our actuator, or the pressure hose and the tank hose are ports. This is actually an air solenoid valve here, so this is for pneumatics. Okay, and you can see it's a two-way, two-port valve with the arrow pointing to that, and this is activating our solenoid and there. Okay, this here is a two-way valve, but 4 ports. So it's two positions. So a way and a port, way and port refer to the same thing. It's a way for the fluid to flow. And then the position is how many positions on the valve. So sorry, it's a 2-position, 4-port valve with a solenoid to activate it and a spring to return it back to the default with that when the solenoid is not activated. This is a this is a 3-position, 4-way valve here. Okay. All right, now pneumatic systems are very, very similar to the hydraulic systems. Okay, the differences here are pneumatics, they actually do use a fluid, but the fluid is air. Okay, they still need a compressor to compress it. They have to have a control valve, they're going to have piping, and they're going to have cylinders, some type of activator. Okay. Where hydraulics, the fluid is oil, so other than that, the general basic structure of the two systems are the same. Okay. Good things about pneumatic power. Pretty much any industrial site is going to have pressured air available, so it's there. So if you wanted to add a new device, it's very inexpensive to add that other device. Air can leak, and it's generally not a hazard as long as, you know, like when the leak pops, it doesn't blow pieces flying or whatever, but just little leaks here and there are not going to have oil laying around that can be slippery or hazardous to try to move across, and it's not going to catch on fire. All right. Pneumatic systems have a pretty good response time, so they're, like I say, they're quite often used for small actuators, like on grippers on the robots, and pretty good for use for pick and place kind of uh, applications. All right, now some downsides. Number one, that you do have to condition the air. You have to remove all the oil and moisture and impurities out of the air. You got to maintain the air pressure. Um, Another part is the fact that because it's air, it's compressible, and so therefore you can't get very good precision control out of these actuators because they'll compress, and so they do have some limitations there. Limitations, excuse me, some limitations on there. But like I say, the pneumatic systems are typically used for grippers. They're very common on standard grippers, finger grippers or vacuum grippers, which vacuum grippers are used quite often, and those of course need air. So I guess that's about it for this set of slides. Like I say, there's several links in there. You want to check out those links